Very good. Thank you for keeping to come to the class. I'm really pleased to see you. How does it progress?
Not sure yet. So you said alpha is 2?
Alpha is 2. And do not care about first column, process the last one, the third.
What?
Huh? Just like e to the alpha square will be e to the minus 4, just some small number you can keep it. Process this last fraction. Like 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, right? And like 2 to the power 0 is 1, 2 to the power 2 is 4, 2 to the power 4 is 16. So while you are entertaining this exercise, I'll give a heads up of what are we doing. So by the end of the meeting, it would be really great if we come to the common decision about the time of the presentations. You saw the email, so there are rooms reserved both this Friday and coming Thursday from 10 to 1, and this Friday from 11 to whatever it takes. And before we leave, we will raise hands for either one or another date, and Steven either will put a microphone on or send an email. So there are this night, but by midnight, I will be expecting final versions of the reports on the project. Please send them in the Microsoft Word. Some of you send them in PDF. It will be very hard because this local company who composes the community booklet do little formatting and copy editing, putting page numbers, squeezing or expanding figures, and it's much easier to have it homogeneous. This night, not night, evening, we'll make sure that everyone has movies ready for the presentation because it's so much easier to just look at the movie. I'm done. And today's lecture will contain cool material there. It will be like a top of the cherry on the cake. It will be based on many concepts that we have covered during the class, and it will lead into prediction of the electronic vibrational spectra, the shapes of the absorption spectra, predicted the sufficient level to match some experiments. And before going this, you already customized. The thing that you are doing is for absorption spectrum of paper and all. These numbers will be used. And I noticed from previous years that if I assign 1 minute for this table, it's not possible to go over to the video. Now you will before we start with this lecture material, I'll do a couple of comments for Alyssa and Morgan as primary customers, but in some sense, this lecture is for them anyway. So for Morgan, it will be just a concept of combining together of electronic and nuclear degrees of freedom into one system that we are doing. Alyssa did it as well. And this will be the essence of spectra of molecule, visible spectra of molecule that we cover anyway. And there is another thing that doesn't much my original content. It was a question from Alyssa about atomic terms. Some of you may have been exposed to inorganic chemistry or freshman chemistry, how to name electronic state of multi-electron atom. And I'll just quickly cover this. You will feel comfortable. Is it possible to summarize this effort towards spectrum of atom form? Yes. If we keep in mind, there are many molecules with similar shapes of the spectrum, but if you think about soft diatomic with at least 2 electronic states, the idea is that even if we consider only 2 electronic states, ground and first excited, each electronic state has many sub-levels depending on quantization, quantum number of vibrations. And there are transitions that affect not only the electronic quantum number, but also the quantum number of vibrations. And these transitions do have different energy offsets, and they have therefore they will be responding to a quantum of different frequency. And they have different matrix elements of transition. They will have different intensity of absorption depending on frequency. So the 2 electronic states for diatomic molecule will have spectrum much more complicated than just one line for transition from these 2 states. There will be complicated shape that looks like a count, like fat counts of overlapping sticks. For processing this idea, one needs to factorize wave function, as we did for 2-dimensional particle in the box. Like there is one dimension, wave function along x, and there is another dimension, y, and there is a wave function along y. Overall wave function is product. Now our x and y will be electronic wave function and nuclear wave function, that they are a product. And if we are looking for transition, it will be transition from one product, electronic and nuclear, to another product, electronic times nuclear. And if we apply several concepts from our class to this idea, we will get complicated profile absorption. Okay. This was a summary. Last academic lecture we did something about spin, geomagnetic ratio, and rotation in the box here. And this little equation is, I'm so happy that Morgan is here. This is your equation. It's not the, I was not a mock reviewer of your work, but when I will look for the final one, I will look for this equation in your report. What does it mean? If we propagate, if you solve something in quantum theory, we always have custom to have Hamiltonian. And if you do have 2 electronic states, let's say alpha and beta, they should be in Hamiltonian. And you remember from this game with spin, the Hamiltonian is projector on state alpha times energy of one state, projector on state beta, and energy of another state, which are constants. It is like spin or 2-level system. But if we do have nuclear degree of freedom, the energy of electronic state alpha and beta, or 1 and 2, will depend on position. So potential energy surface for state 1 or for state alpha and state beta will be a function of position. And it is one of the typical ways to store the energy for such hybrid systems that have both electronic and nuclear degrees of freedom. Kinetic energy is only for nuclear degrees of freedom is the same, but potential energy is depending on position. And for Morgan's case, it will be 2 parabolas which are offset in both x and y. for Alice's case, there will be more than two, like four potential energy surfaces, and they are more potential. Some of them are conservative, that keeps molecule, and another dissociated, that breaks it into pieces. But same idea, mix together in one electronic, both electronic and nuclear. So, answer to question by Elisa. What you are asking? What is the symbol 2 in the upper 2p1/2, something like that. So if you do have an atom with many electrons, not hydrogen atom, but like iodine, there is a Aufbau principle, like how you fill the electronic shells, and there are contributions to angular momentum of overall atom from both orbital cycling of electrons, and if there are several electrons, their angular momentum can add or subtract. Plus, the spin is also, nature of spin is angular momentum, and one can add or subtract orbital angular momentum and spin angular momentum. So one needs to, if one has multi-electron atom, one needs to specify three things: spin angular momentum, orbital angular momentum, and total angular momentum, which is typically orbital minus spin. And there is a Wikipedia, relatively good Wikipedia article on that. So the orbital, instead of spin, one puts degeneracy, which by 2s+1. If s goes in fraction of integers of 1/2, like for spin 1/2, it will be 2 times 1/2 plus 1, 2, which means double degeneracy, the up and down. If spin is 1/2 plus 1/2, 1, then 2s+1 will be 3, triple, the up, down, and in the middle. J is typically like subtraction or summation, because there's atom can be in several states. So the example which may relate to what this is doing, you all know that there is a website that's called ptable.com, right? And there is a button orbital. So if you click on the atom, it shows how the shells are filled. And if you click on specific orbital for quantum numbers, it draws the orbital. So if you look on the iodine, you see everything is filled up, down, except the 5p, which has 5 electrons, well, maximum is 6. So I'm going to zoom in only onto this little thing. Even narrower. So the orbital angular momentum, and we have several experts in the room. Angular momentum can correspond to rotation clockwise and counterclockwise. Right? If it goes clockwise, angular momentum, and in units of Planck constant is 1. If it goes counterclockwise, -1. If it is like superposition in between, it is 0. Now, if you have several electrons, like 2 electrons have different spin, but their angular momentum corresponds to this cell, which means angular momentum -1. So -1 times 2. Two electrons here, 0 times 2. 1 times 1. So you get -2 plus 1 will be -1. Absolute value is 1. So angular momentum is 1. So it is P. But since it is multi-electron state, it is P capital. I'm going to jump back to 2 slides. So depending on the angular momentum, 0, 1, 2, 3, if it will be S, P, D, then most of it repeats out. So instead of L, we will write capital P. Now, these spins are paired, only one unpaired spin, spin 1/2. So it's S equals 1/2, 2s plus 1 double. Orbital, which is 1, minus spin, which is 1/2, will be 1/2.
So if it would be 3 halves, then it would just be, it would not be a
summation L plus S. So it can take, the system can add angular momentum, orbital and spin angular momentum in any combinations between L minus S to L plus S. And they will be different orthogonal Franck states. So the lowest state will be 2 doublet P 1/2. And the next state will be doublet P 3/2.
Wait, so how do you get the 3 halves?
If instead of minus you put plus here.
And you can just do that?
Yes.
Okay.
So at least there is something.
Okay. I'll read more about it.
Okay. So the things, the numerical things that you're processing will be the height of this elements of a count. And I will have something better to show, a little bit better figure. Stokes shift, you know, right? So absorption and emission of a molecule looks symmetric. And if you have absorption, the emission will be a little bit mirror reflection. In case quantization of nuclear motion is negligent, transition, either absorption or emission between two electronic levels will be just one line corresponding to their energy offset. But if there are transitions increasing amount of nuclear vibrations or decreasing, it will be absorption, it will increase by the amount of vibration quantum. For emission, it will be decreasing. And the intensity of each transition will be different. So the goal of today's meeting is to get this shape. And in some sense, you already fulfilled it by filling the table. Okay. I took the parameters, I took Morgan's code and just slightly modified. So if one finds eigen energies, they are offset from 0. If one finds eigen vectors, they are shapes. And there are two sets of orbitals. One that looks like harmonic orbitals for ground state, G, and they 0, 1, 2, 3, and another set in numerical solution of let's call it Morgan's Hamiltonian. They are counted continuously and they are intermixed. But as humans, we can identify that part of the states, they color them as blue, filled with one potential, another set. You see this one hump camel, two hump camels, they are in red and they offset by the same energy. They are placed in the red direction. And we can call them excited 0, 1, 2, 3. So G or E stands for electronic state. Integer numbers stand for quantized state. The goal of today's meeting is to consider this system being in the ground electronic ground nuclear state, being subject to electromagnetic irradiation, and explore at which frequencies, with which intensity this molecule is absorbing electromagnetic radiation. The outcome will be here. It is the same thing which was on the previous slide, and it is the same thing that you are doing. You'll have that by now. So, this one is not the lecture. It's just expected outcome. I'm not sure if there will be time for derivation, but it is only show of the results. But the optical transitions inside the blue parabola are not possible because this quantum states within one parabola are orthogonal to each other. It's one state. We have electronic transition from blue to red. So the lowest transition will be from G0 to E0 here. So if we try to excite this quantum of frequency below this transition, it will be nothing. So the lowest transition from G not to E. And in addition to factors like oscillator strengths and resonance frequency, in order for this transition to be possible, the shape of this wave function, the shape of this wave function must have non-zero overlap. Since they belong to different electronic states, they do not need to be orthogonal. They may have non-zero overlap. And the amount of their overlap, which can be symbolized by bra times ket squared, will provide the intensity of the optical transition at given frequency. Next available transition is from G0 to E1. So from this one hump camel to two hump. If we compose this G0 in E1 overlap, you see that this two hump camel moves a little bit towards this value of position. And intuitively it is seen that it has better overlap. Therefore, this transition is more intense. So from G0 to E2. So this peak moves closer, even closer to the spatial position of the vibronic state G0, and overlap here is even bigger. So it's the most intense point. If you go further to the third excited state, the overlap of this hump here and there is also rather quick. But area under this hump is 1/4 of overall wave function. So the total amount of overlap will be a little bit smaller. So the intensity decreases. And if you go further, the overlap between humps becomes smaller because this far rightmost peak shifts to the right from the center, and it becomes smaller fraction of overall wave function that is distributed in a bigger expanse or bigger space. So it keeps decreasing, smaller and smaller and smaller, and then decreases. So there is a optimal intensity where it absorbs most. So the goal of today's meeting is to find a way to predict shape of the spectrum informed by pen and paper calculations and some concepts based on what we did in the class. So beginning the lecture, and we have 15 minutes. That's deep. So potential energy surfaces generally do not need to be parabolas. They can be Morse potentials, more similar to what I was saying. And they are very often offset by the energy vertically and by the position of the medium horizontally. Therefore, optical transitions need to take into account the optical quantum of light needs to be in this resonance conditions. So the energy of ground minus energy of excited depends on the position. And since nuclear motion is quantized, we cannot just explore each point and explore each transition. It's possible, but it is a strong approximation. Why electronic state is changing. The closest expert to this aspect is Russel. The molecules have dipoles, especially polar molecules, but even non-polar molecules have so-called transition dipole. Right? So matrix, the dipole is vector connecting positive negative charge, and any dipole does interact with electric field. If it is quickly slow electric field, dipole will just rotate towards you. If it is a quickly changing electric field, it will either try to move force back as in plasmonic nanoparticles, or if it is really high electric field, instead of following it, it will just jump to another electronic state. So the dipole is a measure of response of system to electron, and we will add together negative, which are positions of electrons, and positive, which are positions of ions. And the interaction between electric field and dipole is just scalar product, and it's with minus. If it is slow or static electric field, it is minimum when they are aligned. So, in case our electric field oscillates then it promotes from ground to excited. And the transition from ground to excited will be proportional. It's not, we can't cover all details, to the matrix element of the dipole operator between ground and excited electronic states. So we are fine with concept of matrix elements, and we intentionally explored matrix element of position operator, which is a part of dipole, when we studied particle in the box. You remember this? It was probably the hardest homework. So it was all intention, preparing for today. Now, close your eyes and do not watch, because there will be too many variables. By the way, I do not have time, but I really want to invite everyone to join course in computational chemistry in the spring if your schedule allows. It will be 10 times easier, 10 times more useful for research and career. So, generally, wave function depends on positions of electrons and positions of nucleus, and it is a very big wave function of many, if it is many electron and many ion molecule, it's like really huge object. And one can factorize high electronic and high nuclear degree of freedom. And then the interaction with electric field will be operator of interaction, and then bracket. So wave function initial and final, right? With understanding that initial and final can be factorized on electronic degree. And this matrix element between initial and final is referred to as transition dipole, because we are in transit from one state to another. So, what do we do if we have found the operator? We practice Fermi's golden rule. Give me a little sign if you never heard about it. So it's okay if you didn't, because one needs a few more chapters to rigorously derive it. But if there are transitional phenomena, transition from one state to another one, the in the lowest order of perturbation, assuming that all fields are small, the transitions are going linear, or wave function changes linear in time and population quadratically in time, with the rate of transition of state 1 to state 2 is matrix element of transition squared times density of final states. If the final states is degenerate and there are more of them, it will be quicker. And this is common rule that can it is oversimplified, but it works almost in all cases. And it is applicable to optical absorption. If you apply Fermi's-Golden rule to optical absorption, we plug here transition dipole, put it squared, and multiply it by density of final state. In community of experimental spectroscopy, theoretical spectroscopy, transition dipole moment squared times some few additional factors is called oscillator strength. So this Alyssa was finding it in Gauss and had an output. So this intensity of transition at certain frequency. Okay? So it is transition dipole matrix element squared. If we do want to practice theoretical spectroscopy in the remaining 8 minutes, we can do the initial and final state with only one electronic degree of freedom and one nuclear degree of freedom factorized. And since you are experienced and almost certified experts in physical chemistry, you do know that any function can be expanded in a basis of eigenstates. So electronic function can be expanded as expansion coefficient on the wave function of ground and excited. And some other excited 2, 3, 4. But instead of processing the functions, we can process only expansion coefficient. Right? The nuclear wave function can be also expanded in terms of states of nuclear wave function, which can be considered as an oscillator if we are close to equilibrium. So instead of writing down explicitly those functions, we just need a number of eigenstate and expansion coefficient. Okay. So what we do is correct for most diatomic molecules. And then the matrix element for this interaction transition dipole will be one electronic, one nuclear, another electronic, another nuclear. And the electronic and nuclear will be labeled by, electronic will be labeled by E and G, and nuclear will be labeled by M capital and N capital. So each of these states, products, electronic and nuclear, will have its own energy. It will be just energy for electronic state plus so many nuclear quanta. And their offset will be the subtraction, which must be in resonance with optical field. And the absorption can be considered as a particular example of Fermi's golden rule. So summation of density of states, which is density of these energies, as we did density of states, but they are intermixed. They need to be not just in resonance, they need to be in resonance with optical transition. So the optical field kind of brings initial and final to the same energy. And the intensity will be a factor that depends on all 4 quantum numbers. 2 electronic quantum numbers and 2 nuclear numbers, which we call oscillator strength. The difference in this delta function, so energy of one electronic state, energy another electronic state, number of vibration of quantum, number of excitation plus 1/2, number of excitation plus 1/2. So the energy of set will be difference plus frequency of vibrations and difference in vibration of quantum numbers. If it is 0-0 transition, this term will disappear. If it is 0 to 1, it will be offset by 1 vibration. So matrix element. When we form transition from one electronic state to another electronic state, our operator, and here I appeal to experience of charge. The operator will be a position operator in respect to electronic degrees of freedom. Since we have more than 1 degrees of freedom, the operator should be like bigger. And the right form. But in respect to nuclear degrees of freedom, it will be identity operator. So we do not change anything in nuclear degrees of freedom when we photoexcite, because we do it so quickly that nuclei do not have time to change. We just project, promote it up, even the same shape. Okay? So it is unity operator in respect to nuclear. And then we have ground and excite. But for nuclear degrees of freedom, we start with ground state in original, in ground state, and some other quantum state M in the final state. This is the letter M in the chart that you were filling. So we're going from ground to excited electronically and from 0 to M in sense of vibration. This matrix element includes 2 integrations. One integration over electronic degrees of freedom and one over nuclear degrees of freedom. The one that is over electronic degrees of freedom can be factorized. So electronic wave function, transition dipole, electric field. One can compute it once forever. And if you have a transition dipole, for example, that comes from Gaussian computation. But in addition, there is a second part. Initial nuclear wave function, final nuclear function, 0 to M. They are eigenstates for different parabolas. And they have unity operator between them. So this operator is just nothing. So we do see just overlap of 2 nuclear wave functions that you saw in this colorful chart. So the goal, and this is called Franck-Condon factor, that contributes to intensity of optical absorption. And our goal in the remaining whatever minutes is to get a formula for this Franck-Condon factor, which will depend on the M. So any quantum state in the eigenstate of harmonic oscillator is can be obtained by applying creation operator several times. The ground state, parabola in the lowest, is promoted to the next parabola, and then it can be considered as coherent state in the upper parabola, that we need to expand this Gaussian from lower parabola or eigenstates of second parabola. And this overlap will be nothing but eigenstate in ground and lower, and this expansion coefficient that's come from definition of eigenstate of annihilation operator from a coherent state that are known. We did it whatever 20 lectures ago. And this is Franck-Condon factor from vibrational state 0 to vibrational state F. And if you need an absorption spectrum, we do resonance condition and a matrix element that depends on this Franck-Condon factor. And since intensity is this stuff squared, we can go into dimensionless things and take typical values. Alpha will be equal to. And now I appeal to your table, which I don't have time to complete. So this is number of vibration progression. This is energy offset, which will be just delta E plus 0 plus h bar omega plus 2 h bar omega plus 3 h bar omega. And here will be numbers that are growing for the first 2 or 3 things and then decreasing, if you see. When I was doing it, my numbers were something like e to the power minus 4, and then the numbers 4, 8, 10, 10, 8, 6, 3. Maybe your numbers are slightly different. But if I plug in these intensities, these Franck-Condon factors, into the chart, energy of cell intensities, and then I dress each of the transitions with Gaussian distribution as we did for density of states, then there will be this shape of absorption spectrum. So absorption is blue shifted, emission is red shifted. And then we have the same thing as we saw at the beginning. Thank you for your patience and staying here. And who is for Friday? One?
This Friday?
Yeah, who's for this Friday? 1, 2, 3.
I have no opinion.
Okay, 3. Who is for coming Thursday? 1.
I'm okay with it. Yeah, honestly.
So 3 to 1. Majority prefers this Friday. Steven, would you be able to come on Friday? Maybe not sharply at 11, but slightly later. Okay. So by now it looks like the majority is for Friday. Would you be able to compose like 5 minutes long presentations based on your reports?
5 minutes long?
Yes. No longer than 5 minutes. You will be maybe tortured for another 5 minutes by visitors, but do not make it long.
Yeah.
Okay. No pressure from my side. By democratic procedure, 3 to 1 votes, we accepted Friday. Right?
Yeah.
So Friday 11, and then you are having 2 remaining tasks: written reports this night, slides next night, Thursday midnight, because I need to put them into a computer, otherwise it will be big mess and disorder of everyone uploading from memory stick. Okay, and then you will be free for the final speak, free of me. Okay. If we will be so busy in the remaining time,